All right, so this is chapter 21. Problem number 26. At number 26, we have a person with body resistance between their hands of 10 kilo ohms. The resistance of this person is 10 kilo ohms. What is that in ohms? 10 to the third, 10,000 ohms. They accidentally grasped the terminals of a 20 kilovolt power supply. So 20 kilovolts. What variable would go in front of that? What is that? What physical thing is that measuring? Voltage. Go figure. V stands for voltage. Kilovolts. Okay. What would that be in just plain old volts? 20,000 volts. It also says in parentheses for you, do not do this. Don't grab a battery that's 20 kilovolts. Okay, draw a circuit diagram to represent the situation. And part B, if the internal resistance of the power supply is 2,000 ohms, what is the current through the person's body? Part C, what is the power dissipated in the body? And part D, if the power supply is to be made safe by increasing its internal resistance, what should the internal resistance be for the maximum current in this situation to be 1 milliamp or less? And finally, will this modification compromise the effectiveness of the circuit? Lots of stuff there. Part A, draw a picture. So what things do we have inside of this circuit? We have a battery. How do I draw a battery? For those on YouTube that are listening to this and can't see, they're all drawing little lines in the air. We have a little line here and a longer line there. So there you go for a guy in India watching this. What else do we have in this circuit? Do we have a particularly smart person in this circuit? No, we have a very stupid person that is grabbing two ends of this battery. So we can represent that person. We'll just draw a circle to represent that. What's the voltage of the battery? 20,000 volts. What's the internal resistance of the battery? My resistance, the resistance of the person, is 10,000 ohms. The internal resistance of the battery. So every battery has some resistance. So there's a little resistor inside of that battery. That resistance they give us is 2,000 ohms. So there's my picture. Squint and you can actually tell what I just wrote. And Part B wants us to find if the internal resistance of the power supply is 2,000 ohms, what is the current through the body? So I have a V, I have an R. How do I find the total current? Whose law can I use? Ohm's law. Ohm's law. I have always memorized V equals IR, so this is always what I work from. How do I use this to find the current? Algebra. I equals V over R. So I need to take the voltage and divide by the resistance. What is the total resistance here? 10,000 plus 2,000. So the total resistance is 12,000. What's the total voltage? 20,000. So 20,000 divided by 12,000 gives me my current. I divide those two numbers, I get 1.67 amps. I'm also asked, what is the power that's dissipated in his body? So what is the power that is flowing through this person? How do I find power? P equals I squared times R. What's the current that's flowing through this circuit? What current is flowing through this dude? The 1.67 amps. And we square that number. And what's the resistance of the person? 10,000. Why aren't we using 12,000? It's asking just about the person. It's not asking about the whole circuit. If I ask you what's the power dissipated in the whole circuit, then we'd use the 12,000. Because we just want what's happening to the person. This stupid idiot that just murdered themselves. So I multiply these numbers all together. I get 2.8 times 10 to the 4. What are the units on that? Watts. Again, a watt is a joule per second. And then part D, it wants to know what kind of resistance do I need in this circuit so that my current ends up being, I think it's 1 milliamp. What is a milliamp in amps? What is milli? That's a really bad 80s singer. The 80s? Was that 90s?
They weren't really singers.
They weren't. They were really bad singers.
They were lip syncers.
Do any of you know this besides me and Carrie? Milli Vanilli? What do you know about Milli Vanilli? They were lip singers. It was a big deal. They could dance really well, but they couldn't sing.
What song was it?
They had a couple songs, right? After I do lecture, we'll play some of their songs on YouTube. I'm sure we can find them. So we've got a milli. What is milli? 10 to the negative 3. 1 times 10 to the negative 3 amps. One nice thing is that if you answer my questions right away, then I don't go off on tangents. Okay, what's the voltage in the circuit? I still have the same battery.
20,000.
Still 20,000. And I want to know what resistance do I need to have this be true. So how do I figure that out? V equals I times R. I want to know what resistance I need. So I take the resistance equals V over I. So I do 20,000 divided by 1 times 10 to the negative 3 amps. The resistance here would be 20 times 10 to the 6 ohms. Your book might give that answer as 20 mega ohms. 20 million ohms. And that's not an odd number for a resistance. Resistances can be quite high.
You only asked us to do it till C. Are we supposed to also know?
I only ask you to do to part C?
Yeah, yes.
Oh, how nice of me. You should be able to do part D as well. Part E, whatever. Part E, you don't need to know. Okay, so that was problem number 26, I believe. Any questions on that one? Yeah.
How did you know which power equation to use? Is it just based on the variables of what you're trying to solve?
Yeah. So you could use P equals IB, but you need to know the exact current and the exact voltage that's going through the person to get the power.
Which would be more.
Right. Okay. Any other questions? No other questions on that one? Okay, so now we're going to go backwards, and we're going to do problem number 7. Problem number 7 is a long one. There's a lot of parts to this. And what I'm going to show you is a general approach that you can use to solve any of these kind of adding up resistance problems and figure out every single element of the circuit. So I can find the voltage, the current, and the resistance through all pieces of all parts of this circuit. And I do that by taking the circuit and simplifying it to be one resistor, and then I work backwards from there. And I'll give you some strategies to do that. So problem number 7 in particular tells us, referring to the example combining series and parallel circuits in figure 21.6, calculate I3 in the following 2 different ways. So they want you to use a specific approach. I'm going to do this like I gave it to you on an exam. So I'm going to give you a circuit. I'm going to ask you to find things in that circuit. I'm not going to tell you specific ways to do it. I'm just going to tell you, look at this circuit and find the currents through all pieces of it. So I would give you something like this. Here's the picture. We have a resistor. Okay, I'm given a voltage equal to 12 volts in the battery. Resistance 1 is equal to 1 ohm. And there's some current flowing through that. I don't know what it is. Some current I2. I don't know what that is. Going through this resistor, it's going to be 6 ohms. And then some current I3. I don't know what that is. And resistor 3 is 13. What else do they give us? They give us from the example, they tell us I2 is 1.61 amps and the total current is 2.35 amps. So they give us this. Well, we're going to find out how to do this without knowing that. So we want to find what are the currents through every single part of this circuit. And to do that, what you do is you take this circuit and you simplify it so that it's only one resistor. And then once we have it as one resistor, we'll work backwards. So I'm going through this circuit. I go up through the battery. I go through the first resistor. Fine. I keep going. And then I end up at this part where the current splits off. So can I add R1 plus R2 plus R3 all as one? No, why not? Because this is series and these two are parallel. So first I need to combine these two that are parallel into one resistor, and then I can add that one resistor with this one in series and get it all the way down to 1. So let's draw that. Let's draw what that looks like. So here's my battery. I go through my first resistor and I combine these two into one. So I need to figure out what this combination is. I have R2 plus R3. So I'm going to call this resistor, this equivalent resistance, R23. And I still have R1 and I still have my voltage over here. How do I find R23? These are in parallel. How do I add resistors in parallel? Do you just add them or add the inverse? Parallel, you add the inverse. So 1 divided by R23 equals 1 over R2 plus 1 over R3. So 1 over R23 is equal to 1 over 6 plus 1 over, I believe it was 13. So go ahead and take out your calculator and tell me what you get when you add those. What'd you get? 0.24. And then what do I have to do with that? Inverse. Have to flip it upside down. R23 is equal to 4.1 ohms. Now, can I add R1 and R23 together? R23 is in series with R1, so I can combine those two and turn it into one resistance. So now my circuit looks like this. I have a V, I have an R, and that's it. V, R1, 2, 3. R1, 2, 3 is going to be R1 plus R2, 3, that equivalent resistance that I just found. So R1, 2, 3 is equal to 1 plus 4.1. R1, 2, 3 equals 5.1. Yeah. Does all that make sense? Yes. Don't worry about AC circuits. AC circuits, we're not going to do any AC circuits. That's for capacitors. Capacitor is different than AC. AC stands for alternating currents. Yeah. Capacitors are flip-flop resistors. Okay, so I've got this simplified into one resistance. Now I can work backwards and I can find everything I want to know about each part of this circuit in turn. So I know in this circuit, I know V. What was V? V is 12. So I know V1, 2, 3 is 12. R1, 2, 3 is 5.1. What else can I find? I can find I. I is V over R. So that's going to be 12 divided by 5.1. So the total current is 2.35 amps. And now I can take that and I can work backwards. So when I'm working backwards in these circuits, there's some things to keep in mind. I, if you're in series, is the same. And V, if you're in series, splits. We'll talk about what that means. So I know the current here is 2.35. I go back one step. My resistors, are they in series or are they in parallel? They're in series. So because these are in series, the current that I had before I went backwards, that's going to be the same current that goes through each part of that. So now I know, because I in series is the same, I know I1 is 2.35. I know that I23 is 2.35. What else can I find? I know the resistance, I know R1, I know R23, I know I1, I know I23. What's the third variable? The third thing to find here. Do I know V1? Do I know the voltage going through the first one? No. And I don't know V23. I want to find the voltages going through each of those. So how do I find the voltage going through I1? Do we know R1?
Yeah.
What's R1?
1
R1 is 1. If I know V and if I know R and I know I, how do I find V? V equals IR. V1 equals I1 R1. So V1 is 2.35. R23. What was R23? So what's V23? What's 4.1 times 2.35? 9.64. I'm going to round to 9.65. It's close enough. I'd show you another way that we can find it. How much voltage is going through this whole circuit?
12 volts.
12 volts. The voltage gets split between R1 and R2. If there are 2.35 volts going through R1, and I can take 12, the total voltage, minus the voltage that's through this first resistor, and that gives me the voltage through the second resistor. So it's all consistent. Yeah. 12 minus 2.35 will give me 9.65, or I times R. Now I work backwards again. I work from everything I know in this part, backwards one more. I know everything about R1. I don't need to solve anything else there. I know R1, V1, I1. I don't know things about these ones. If I go backwards, I go from R2, 3 being one circuit, one resistor, to being in parallel. So what do I know about the voltage through each of these? Same voltage. So whatever voltage is going through R2, 3 is the voltage going through R2, is the voltage going through R3. What do I know about the current? Current is going to split. Some current's going to go through one side, other current's going to go through the other side. I in series is the same, V in series splits, so the opposite is true as well. I in parallel is going to split, V in parallel is the same. So you really only have to memorize these two and know that in parallel it flips. Parallel is opposite. So I can go backwards one more step and I can find all these things. I know R2 is 6. I know V2 is the same as V23 is 9.65. So I can find what I2 is. I2 is going to be, what is that, V2 over R2? And when you divide those two, you should get 1.61. And then R3 is 13. V3 is still 9.65. So I3 is V divided by R. You should get about 0.74. There's a lot of stuff here, but it's an algorithm. It's a puzzle. Now I can notice something else about I2 and I3. The current splits between these two. What happens if I add I2 plus I3? What do I get? Add those numbers together. Then you get I1. You get the total current. So all the current, when you take current, it's going through series. All parts of the series circuit get the same current. So when you add up these two numbers, that's got to be the total current. Part of it goes through here, part of it goes through here. 0.74 plus 1.61 is 2.4. So in these problems, there's a lot of places where you can check your work too, to make sure that you're getting the right things. Everything will be consistent. They're neat. I like these ones. So if I gave you something like this, I would give you the picture and ask you to find what's V1, V2, V3, I1, I2, I3, R1, R2, R3. I'm going to give you some of those variables. This is the procedure. Questions on this? It's all on video. It'll be uploaded to the YouTube channel. And there should be a link now on Canvas that takes you directly to the YouTube channel. Yep. All right, let's do another problem. Let's do problem 38. On 38, they give us a Kirchhoff's law problem. So they give us a circuit, and they ask us to find all the currents. So let's just draw the circuit that they give us. They give us this picture. Ooh, they have a lot of stuff in this circuit. Okay. That's the circuit. We've got R1 here. We've got E1 here. We've got little r1. We've got big R5. We've got E2. We've got little r2. We have, oh gosh, I can't read my own handwriting. Little r4. We've got E4. Little r3. Big R3, E3, and what is that? Big R2. And they give us values for a lot of these. They give us E1 is 24. Little r1 is 0.1. Big R5 is 20. Big R2 is 40. E2 is 48. Ooh. It's going to take the rest of class just to write down all these things. Little r2 is 0.5. Big R1 is 5. I'm running out of space. E2 is 6. Thank you. I'm dying. R3 is 78. Little r3 is 0.05. Little r4 is 0.2. And E4 is 36. All of this stuff, all given. This is all known. And they add in one extra thing here. They tell you current 1 is going this way. Current 1. Current 2 is going through that middle portion, and current 3 is going up through here. And they want us to find I1, I2, and I3. Find all the currents. So how many unknowns are there? If I need to find I1, I2, and I3, how many unknowns? 3. If I have 3 unknowns, how many equations do I need? I need 3 equations. I get those equations by using the junction rule and by using the loop rule. The junction rule is current in equals current out. So here's a junction, current coming in and current leaving. What currents are going into that junction? What currents have arrows pointing towards that dot? I3. Any others? No? What currents are leaving? I1 plus I2. That is one equation. I3 equals I1 plus I2. Yeah? Easy enough. How many more equations do I need? 2. How do I get those 2 equations? flip that equation around, that'd be the same equation then. How can I get more? I want more. What did I make them do on the board? Loop rule. I have to draw some loops. So I make some loops in here. Let's make some loops. We'll make one loop. We'll go through the top. And then we'll make another loop that goes through the bottom. So the loop through the top. The way you draw your loops, the way you draw the loops doesn't matter. Pick whatever loops you want. But the way you write them, you're adding voltage when you cross from a negative to a positive side of the battery. You are subtracting voltage when you pass from the positive to the negative. You are also subtracting the voltage across the resistor. When your loop goes in the same direction as the current, you are adding voltage when you're going opposite directions. So we'll see what all that means. So I'm going to start on battery E1. Am I going from the negative to the positive or positive to negative as I cross over this battery? Negative to positive. So what do I do with that? I add it. So I have a positive E1. Then I hit this resistor. I hit this resistor. My loop is going to the right through the little resistor R1. What direction is the current going? So I1 is going the same direction. So do I add or subtract that voltage? I subtract. If they're going the same direction, I subtract. So this is E1 minus I1 times little r1. What sometimes helps me is drawing the current completely through. So that's where I1 is going. These pictures can get very, very busy very, very quickly. So positive E1 minus I1 times little r1. And then I hit R5. Am I going the same direction in my loop or opposite direction to the current? Same direction. And what current is going through that? I1. So this is minus I1 times big R5. And then I hit this junction. At this junction, my current's going to split. In the bottom part of the circuit, what current do I have? I3. In the middle portion, what do I have? I2. So I have I2 going through here. I pass through R2, big R2. My loop is going to the left. What direction is my current going? Current's going to the right. So what do? I add that. So that's going to be plus I2 times big R2. Then I hit the little R2. Am I going the same direction or opposite? Opposite directions. So I add plus I2 times little r2. My battery, am I going positive to negative or negative to positive? Positive to negative. So what do? Subtract. So that's minus E2. And then I hit my junction. I'm trying to get back to where I started. Now I'm going up through the junction. My loop is going up through the junction through R1. So I subtract minus I1 times big R1. And then I get all the way back to where my battery started. So what is all that equal to? That is all equal to 0. That is a closed loop. That equation looks like shit. That looks horrible. Sorry, I should use better language. It looks like shirt. Anybody watch The Good Place? You should watch The Good Place. In The Good Place, they're not allowed to curse. So they replace all the curse words with other words. So instead of shit, it's shirt. Motherforker. Holy forking shirt. I'm gonna work on that. Okay, so this equation, it looks very nasty. Is it that nasty though? I know a lot of these things, don't I? I can plug in a lot of them. E1 is 24. So I'm going to plug in my numbers. 24 minus I1 times little r1. What's little r1? 0.1 times I1. So this is minus 0.1 times I1. minus I1 times big R5. Big R5 is 20. So that'll be 20 times I1. Plus 40 times I2. (24) minus 20 plus 40 plus 0.5 times I2 minus 48 minus 5 times I1. That equals 0. How did I go from here to here? Here to here, what did I do? I just plugged in the numbers. And then I can combine things, right? I have lots of I1s here. I can combine negative 0.1 I1 minus 20 I1 minus 5 I1. I can combine the things that are alike. So I combine those. And this gives me a much simpler equation. That whole big nastiness turns into negative 24 minus 25.1 times I1 plus 40.5 times I2. And that equals 0. I can do the same process with the third loop, with the second loop to get my third equation. I have positive E2 minus I2 times little r2 minus I2 times big R2 minus I3 times little r4 minus E4 minus I3 times little r3 plus E3 minus I3 times big R3 equals 0. So this is the same as this loop. I start here. I'm crossing this battery. That's E2 plus E2. I'm going to the right through little resistor R2, and that's current 2, so minus I2 times little R2. And I keep going through and do that circuit. Same exact way. Okay? You're going to want to go back and do this yourself. We are running out of time, but I am purposely going through this quickly so that you have to go back and make sense out of it. Plug and chug all your numbers in, simplify all your numbers. You get to this wonderful equation, 18 minus 40.5 times big I2 minus 78.25 times big I3 equals 0. Procedure from here. Solve equation 2 and equation 3 in terms of I2. So what does that mean? So equation number 2, we'll keep the color consistent. Negative 24 minus 25.1 times I1 plus 40.5 times I2 equals 0. When I say solve in terms of I2, that means get the other variable by itself. So I'm going to solve it for I1, get I1 onto one side. So I add I1 to the other side. I have negative 24 plus 40.5 times I2 equals 25.1 times I1. Divide both sides by 25.1. And I have I1 is now equal to negative 0.96 plus 1.61 times I2. So I'm solving this equation, getting I1 by itself, so that I'm left with I1 is equal to all of this, so I'm getting an I2 in there. I'm going to do the same thing with I3. Solve I3 in the same approach, same kind of concept, and I'll find I3 is equal to 0.23 minus 0.52 times I2. Now, why do I do that? Because equation number 1, the junction rule, says I1 plus I2 equals I3. It's a long problem. I can now take what I had for I1. I can take this I1 and I can plug it in for I1. Plus I2 equals all of this for I3. So I'm going to plug all those things in. I1 is negative 0.96 plus 1.61 times I2 plus I2 equals 0.23 minus 0.52 times I2. How many unknowns are in this equation? One unknown. I can combine all the I2s and I can solve this. So you combine all of your I2s. And when you do that, you end up with 3.13 times I2 equals 1.19. Divide by 3.13 and you find I2 is equal to 0.38 amps. It's a lot of algebra. It's a shirt ton of algebra. Okay. Now, are we done? No. What else do you have to do? You have to find I1 and you have to find I3. How do I do that? I1 is equal to this times plus this times I2. I plug that I2 in right there. And I get my I1. Same thing with I3. Last thing to point out. When you plug in these numbers, for I3 you'll get 0.03 amperes. For I1, you will get negative 0.35 amps. Can you have a negative current? You can have a negative current. It's no problem. What this means is that way up here at the very, very beginning, I chose directions for my currents. I said that the current is going up. If I get a negative current, that just means that I didn't choose the right direction. The current is actually going down. That's fine. Negative current, no problem. Just means the current is going in the opposite direction to what you chose. Okay? These are very, very long problems. Try them yourself. Try them at home, do the algebra. When you get stuck on algebra, make sure you're writing out all the steps, bring it to me, and I can help you find where you're having trouble. Okay?
Wait, can you go back down the bottom of this?
I can.